Dear students, I have covered part 1 of X-ray diffraction in my previous lecture. Now I am starting in continuation of previous lecture. Today I will discuss about the crystallinity calculation through X-ray diffraction. So if you will see, around 100 milligram of sample is required for X-ray diffraction in order to calculate the crystallinity percent. The particle size for individual particle that should be maximum up to 45 micron. If the particle size is up to 45 micron or below that, you will get very good results. So in this way we get this type of result as you are getting here. So this is for semi-crystalline and the blue one for 100% amorphous. So as you will subtract the amorphous from semi-crystalline part, the above part that will represent the crystalline region. So in this way we can calculate the crystallinity percent, means this is amorphous region plus crystalline region divided by crystalline region into 100. So in this way we can get the crystallinity percent. If you will see the XRD pattern of PET and the silver coated PET, then you will find that most of the peaks they remain same, but only the presence of silver that comes through XRD diffraction. So this is the fundamental of Bragg's law, how the constructive interference takes place. So if you will seeing, this is the wavelength one, this is another wavelength, and they both are propagating with same phase difference. So in this way the constructive interference will take place, and due to that the total amplitude of that wave that will be constructive. If you will see the in case of destructive interference, when the wavelength 1 and second wavelength, when they have the phase difference in opposite direction to each other, the resultant amplitude that becomes 0. So in this way no construction will take place, completely destructive interference will take place. So this is the way how the X-ray interact with atoms which are present in any material. This is the way how to prepare the sample. In individual powder sample particle size would be less than 45 micron. For fiber sample preparation it is a little bit tricky. So fibers are generally weighed first and then cut by a very sharp scissor in a small 25 to 50 ml capacity glass flask. So a person should be very skilled for fiber cutting, and we should reduce the fiber size as low as possible, because 45 micron is not possible in case of fiber, but we should try to reduce the particle size as much as possible. Here we are seeing the kind of scattering which takes place. This is the scattered electrons, these are the back scattered electrons, and this is the characteristic X-ray which is coming by the exciting of a particular surface in presence of very high voltage. So this is a development of X-ray diffraction technique to make the quantitative analysis of model amount of minerals to establish crystal structure using the Revelt refinement, the characteristics, various type of thin films samples by determining the lattice heterogeneity between film and substrate, and to determine the dislocation, density, quality of film, rocking curve measurement, and so on. These are the strength of this technique. X-ray diffraction is very powerful and rapid technique for identification of any unknown mineral which is required very less time, means less than 20 minutes to identify the sample. This is very useful technique for identification of various type of minerals in different unknown samples. This is very straightforward technique, and the minimum sample requirement is required. And for fibers type of sample, suppose you prepare the sample, Then after the X-ray diffraction, there is no morphological changes takes place after X-ray analysis. So same sample can be used for thermal identification, particularly for DSC and TG. So if you have to do all three experiments, we should start from X-ray diffraction. These are some limitations of this technique. Homogeneous distribution of powder sample gives the best result. If you don't have homogeneous distribution, you will not get good result. The single phase material is best suitable for identification, but the double phase material and you can say the 2.5 phase material, they can also be identified by X-ray diffraction successfully. Some standard files are needed to subtract the amorphous region and to match with different unknown material with known materials. So nowadays various X-ray manufacturers, they are supplying a very good data bank in terms of standard sample diffractograms. This technique requires 100 milligram of grounded material in powder form. The unit cell determination and indexing of pattern for non-isometric crystal containing material is quite complicated. Peak overlapping sometimes create complexity during interpretation of data. The sample preparation for X-ray diffraction, I have already discussed this one a little bit. This is very latest technique, online X-ray measurement of melt spun fiber. This is developed by a group of scientists. So this goniometer, this is fixed in a spin line and that can move upward and downward direction. So 8 mm to 68 mm centimeter movement of this goniometer is possible with a step of 1 mm. So in a running melt spinning line, the crystallinity percent, orientation factor, crystal size, everything can be calculated successfully. So this is, you can say, very big breakthrough in the field of fiber manufacturing technology. The crystalline orientation. The X-ray is the very promising technology to find out the molecular orientation, particularly in textile fibers. And molecular orientation is calculated in terms of Hermann's orientation factor, and generally the Hermann's orientation factor lies minus 0.5 to 1. So if Hermann's orientation factor is 0, it means the sample is completely unoriented. If the value is 1, it means all molecular chains are completely oriented towards the fiber axis. If value is minus 0.5, means sample oriented in transverse direction, such as perpendicular to the fiber axis in textile fiber. If you will see the X-ray diffractogram of some known textile fibers or some natural fiber which are very popular, you will find this the green one is kenaf fiber, blue one is hemp fiber, and red one is flax fiber. So here you can see the flax fiber is showing very sharp peak in comparison of hemp and kenaf. So you can just see the in case of hemp fiber, the peak is not very sharp, and kenaf fiber is again comparatively little bit sharper peak in comparison of hemp. So if you will calculate the crystallinity percent, you will find different values of hemp, flax and kenaf crystallinity. These are some other samples, like this is untreated rami, this is mercerized rami, this is air dried soda cellulose complex 80% NOS treated rami, and this is rami which was treated at 300 degrees centigrade for 1 hour. So if you will see the all three upper one samples and the lower one sample. Lower one sample means that was treated at 300 degrees centigrade for 1 hour. It means the crystallinity has been disappeared from the sample. So all crystals, they have disappeared. Either the fibers material has disintegrated or it's burned. So if you will compare the air dried soda cellulose complex 18% NOH, this is again indicating the soda NOH 18% caustic soda is reducing the crystallinity percent of the fiber. It means the caustic soda is disturbing the morphology of rami fiber. because the crystallinity percentage is approximately half of the untreated Remy. So this is the conclusion. The X-ray diffraction technology offers very high accuracy for de-spacing calculation in crystal unit. This technique is non-destructive, fast and easy sample preparation is possible. This can be applied in situ conditions also. This technique allows characterization of single crystal, polycrystal and amorphous material. Standard X-ray diffractograms are available for thousands of material as a reference for easy and precise analysis of new and unknown material. The X-ray analysis of powder material has become very efficient and precise due to lot of innovations and improvements in this field. And Hermann's orientation can also be calculated by X-ray diffraction technique, but the sample preparation for orientation calculation is entirely different than sample preparation of crystallinity calculation. For orientation calculation point of view, the fiber must bind parallel to each other in the form of a film. As the fiber will displace from each other, the orientation diffractogram will get too much disturbances, and sometimes it becomes difficult to identify also. So fibers should be parallel, they should not be overlapped, but they should remain in the form of a film, not in the form of a fabric. So thank you very much for your patience listening.